In 1995, astronomers found an object that shouldn't be possible. It was too massive to be a planet, but too small to be a star. It glowed faintly in infrared, warmer than Jupiter, cooler than the Sun, and it sat exactly where our models of stellar formation said nothing could survive. Brown dwarfs occupy the gap between the largest gas giants and the smallest stars. Their mass ranges from approximately 13 to 80 times that of Jupiter. Below 13 Jupiter masses, an object lacks the pressure and temperature to fuse even deuterium. Above 80 Jupiter masses, hydrogen fusion ignites, and a true star is born. Brown dwarfs exist in that narrow band where deuterium can fuse briefly, releasing some heat and light, but where ordinary hydrogen fusion never begins. They form the same way stars do. The nebular hypothesis describes how an interstellar cloud collapses under gravity, creating a young protostar surrounded by a rotating disk of gas and dust. Material falls inward, accumulating through accretion. If enough mass gathers, core temperatures rise until hydrogen nuclei overcome their mutual repulsion and fuse into helium. That fusion powers a main sequence star for billions of years. Brown dwarfs stop short. They never accumulate the 75 to 80 Jupiter masses required to sustain hydrogen fusion. Instead, they compress and heat until deuterium, an isotope of hydrogen carrying one proton and one neutron, begins to fuse. Deuterium fusion ignites at lower core temperatures than hydrogen fusion. The most massive brown dwarfs can also fuse lithium-7, but deuterium is rare, making up only a tiny fraction of available hydrogen. Once that limited fuel is exhausted, the brown dwarf dims and cools, glowing faintly from residual heat for millions of years. The contradiction begins with classification. Planets are defined as large, rounded bodies in orbit around a star, stellar remnant, or brown dwarf, but not stellar themselves. A planet forms through accretion in a protoplanetary disk. A star forms through gravitational collapse and sustains hydrogen fusion. Brown dwarfs form like stars, but never ignite like stars. They're too massive to be planets, too dim to be stars. The International Astronomical Union uses the 13 Jupiter mass threshold, where deuterium fusion becomes possible, as the dividing line between planet and brown dwarf. But that boundary blurs in practice. Jupiter itself has a mass of roughly 318 Earths. At 13 times that mass, a brown dwarf weighs about 4,000 Earths. A red dwarf, the smallest true star, begins hydrogen fusion at roughly 75 Jupiter masses, or 24,000 Earths. The mass gap between Jupiter and a red dwarf spans 2 orders of magnitude. Brown dwarfs fill that gap, but their observable properties overlap with both giant planets and faint stars, making identification difficult. Observations have revealed thousands of brown dwarfs since the first confirmed detection. Early searches used infrared surveys because brown dwarfs emit most of their energy in infrared wavelengths. Optical telescopes see them as dim or invisible. Infrared instruments detect their thermal glow. Spectroscopic analysis reveals absorption lines from methane and water vapor in their atmospheres, features shared with gas giants but not with hydrogen-fusing stars. These chemical signatures distinguish cool brown dwarfs from red dwarfs, which remain hot enough to break apart methane molecules. The discovery raised immediate questions. If brown dwarfs form like stars but fail to sustain fusion, why do they exist at all? Gravitational collapse is a runaway process. Once a cloud core begins contracting, it should continue gathering mass until fusion begins. Yet brown dwarfs stop accumulating mass well before reaching the hydrogen-burning threshold. something halts their growth. One hypothesis suggests that brown dwarfs form in regions where available gas runs out before fusion mass is reached. The protostellar disk may dissipate, blown away by stellar winds from nearby massive stars or exhausted by planet formation. Another explanation invokes turbulence and fragmentation in the collapsing cloud. A large cloud may fragment into multiple cores, some of which lack sufficient mass to become stars. A third model proposes that brown dwarfs are ejected from multiple systems during early dynamical interactions, cutting off their accretion before they reach stellar mass. Observational limits complicate verification. Brown dwarfs are faint, especially older ones that have cooled below a few hundred degrees Kelvin. Current infrared surveys detect brown dwarfs within a few hundred light-years, but sensitivity drops sharply at greater distances. We cannot yet determine whether brown dwarfs are common throughout the galaxy or concentrated near star-forming regions. Population statistics remain incomplete. Estimates suggest brown dwarfs may outnumber stars, but the faintest and coolest examples escape detection. Spectroscopic resolution limits our ability to measure rotation, magnetic fields, and atmospheric composition in detail. High-resolution spectra require long integration times on large telescopes, and only the nearest brown dwarfs provide sufficient signal. Mass measurements depend on observations of brown dwarfs in binary systems, where orbital dynamics reveal individual masses. Isolated brown dwarfs offer no such anchor. Age estimates rely on cooling models, which depend on assumptions about initial heat content, atmospheric opacity, and internal structure. The leading explanation combines formation environment and ejection. Molecular clouds fragment into cores of varying mass. Most cores massive enough to collapse form stars, but some collapse with insufficient mass due to local gas depletion or truncated accretion. In dense star-forming regions, dynamical interactions between protostars can eject low-mass objects before they finish accreting. These ejected brown dwarfs become isolated, drifting through interstellar space without a host star. Some remain gravitationally bound to stellar systems, orbiting at wide separations. Others are observed as free-floating planetary mass objects, massive enough to have formed like stars, but untethered to any primary. This model explains both the mass distribution and the observed population of isolated brown dwarfs. It does not require a fundamentally different formation mechanism, only variations in local conditions and dynamical history. The 13 to 80 Jupiter mass range emerges naturally as the overlap between objects too small to sustain hydrogen fusion and too massive to form purely through disk accretion like planets. Future observations could confirm or challenge this view. Next-generation infrared telescopes with greater sensitivity will detect cooler, older brown dwarfs at larger distances, revealing whether their spatial distribution matches star-forming regions or extends uniformly throughout the galaxy. High-resolution spectroscopy of brown dwarf atmospheres will constrain cooling models and test predictions about chemical composition and cloud formation. Wide-field surveys will measure the frequency of brown dwarfs in binary and multiple systems, revealing how often ejection occurs and whether isolated brown dwarfs formed in situ or were scattered. Direct imaging of protostellar disks around substellar objects will show whether brown dwarfs host their own planetary systems. If brown dwarfs form planets through disk accretion, the boundary between planet and brown dwarf becomes a question of mass and formation history rather than a fundamental divide. If they do not, the distinction holds. Red dwarfs, by contrast, represent the lower mass limit for true stars. They are the least massive, smallest, least luminous, and coolest kind of star on the main sequence. Red dwarfs are by far the most common type of fusing star in the Milky Way, at least in the neighborhood of the Sun. However, due to their low luminosity, individual red dwarfs are not easily observed. Not one star that fits the stricter definitions of a red dwarf is visible to the naked eye. Proxima Centauri, the star nearest to the Sun, is a red dwarf, as are 50 of the 60 nearest stars. According to some estimates, red dwarfs make up 3/4 of the fusing stars in the Milky Way. The gap between the most massive brown dwarf and the least massive red dwarf is narrow, only a few Jupiter masses wide, yet it represents the fundamental divide between objects that sustain hydrogen fusion and objects that do not. Brown dwarfs challenge the definition of both planet and star. They reveal that astronomical categories, however precise, represent ranges along a continuum rather than discrete types. The universe produces objects across the full spectrum of mass, from rocky worlds to supermassive stars. Brown dwarfs occupy the region where planetary and stellar processes overlap. They are neither failed stars nor oversized planets. They are what happens when gravity assembles mass in the narrow zone where fusion cannot sustain itself, but formation proceeds nonetheless. And their existence proves that the line between possible and impossible in astronomy depends entirely on where you draw it.